Hello, everyone. Today, our webinar is on power integrity measurements, and thank you for joining us today. If you're interested in any of our other webinars we'll be hosting or to download any of the free resources we have available, such as white papers or application notes, please go ahead and visit testforce.com/academy, and you'll find everything you need right there. Before we get started, I'd just like to let everyone know that this webinar is being recorded and you'll be receiving an email in a few days with the recording. So you can go ahead and share it with anyone you think would be interested or rewatch it at any time you'd like. I'm pleased to introduce Joel Woodward today. Joel works with Rohde Schwarz as an oscilloscope product planner and enjoys low power testing topics, including power integrity. And now, without further ado, I'm going to hand it over to Joel.
Welcome to today's session. As a test and measurement vendor of both oscilloscopes and VNAs, Rohde Schwarz works with a large number of customers making power integrity measurements. Today, I'll share insight we've gained and equip you with knowledge and techniques to make more accurate power integrity measurements.
Oscilloscopes are a fantastic tool for measuring AC attributes of DC signals, including ripple and noise. Today, I'll use a Rohde Schwarz oscilloscope to show measurement results between different approaches. The same techniques apply if you're using a scope from Rohde Schwarz or from some other manufacturer. Inside of Rohde Schwarz, we use oscilloscopes also for measuring power rails. We'll typically look at sequencing, ripple, load step responses, drift over temperature and input voltage, EMI, and efficiency. And at the bottom is a list of probes that we use to customize the scope to make these measurements.
Today, I'll be showing measurements from a Rohde Schwarz RTO oscilloscope. If you are using a scope from another vendor, the same techniques are still applicable. Oscilloscope manufacturers will have certain scopes in their portfolio that are better suited for power integrity measurements. For Rohde Schwarz, it's the same. These scopes typically have lower noise, better FFT capabilities, and other characteristics that allow them to make better power integrity measurements.
A key measurement challenge with power rails is associated with the ever-decreasing tolerances associated with power rails. Even older standards like 5 volts and 3.3 volts may have tolerances that are much tighter now than they were a few years back. Measuring 10% tolerance on a 5-volt rail is really easy to do on any scope. Measuring a 1% tolerance on a 1-volt rail is a really difficult measurement for most scopes in the world, as the noise from the measurement system approaches and in some cases exceeds the value to be measured. If you've taken power integrity measurements for noise and ripple and looking for transient activity, you've probably used one of the 4 measurement methods that I have listed here. We're going to step through each of these and talk about the benefits and trade-off of each approach. Let's step through each method and compare the measurement results. On channel 1, I've connected a standard 10-to-1 passive probe. On channel 2, a 1-to-1 passive probe. On channel 3, a 50-ohm cable with a blocking cap. And on channel 4, a specialized power rail probe.
I'll sequentially connect to a test board using each one of the methods described on the last slide. This specific test board has a 3.3 volt rail that we can measure across a bypass capacitor.
Oscilloscopes include automated measurements with statistics that makes it really easy to measure worst case peak-to-peak voltages, maximum voltages, and minimum voltages. Infinite persistence allows teams to better visualize the waveform over multiple acquisitions, in addition to the automated measurements that are shown. The results for automated measurements will be identical whether or not infinite persistence is on or off. Let's take a look at the first approach, using a 10-to-1 passive probe, these are the probes that typically ship with new scopes, and hence they're readily available. Other than the fact that you likely have many of these laying around, what are some of the other advantages and disadvantages of using a 10-to-1 passive probe for power rail measurements? First, they have excellent loading at DC of 1 megohm. It means that the DC value is going to be preserved. Second, they're easy to connect. There's lots of different ways that you can connect and ground them. What are some of the disadvantages? A primary one is that they have a 10-to-1 attenuation ratio, which means that you're going to have more noise in your measurement. They are also bandwidth limited, typically to 500 megahertz, and there are not alternatives for doing a solder in to make a consistent, reliable connection.
I've connected the probe ground using an Alligator clip to a very convenient spot on the board. The scope shows the rail at about 3.1 volts, so it's close, not quite exact as what I expected, but it's close. I know I'll get a better measurement if I can zoom in vertically and use more of the scope's ADC resolution. So let's go ahead and do that. I have my scope set at 50 millivolts per division. With 10 vertical divisions, it's 500 millivolts full screen. We're measuring approximately 69 millivolts peak-to-peak voltage. The higher 10-to-1 attenuation ratio of the probe produces more noise. And while the long Alligator clip is extremely convenient, it causes larger ground loop and adds to the noise. Measurement noise is a function of vertical scaling. If I move to a more sensitive vertical scale, I can now measure lower peak-to-peak voltage. In this particular case, I've gone to 10 millivolts per division or 100 millivolts full screen, and I'm now measuring 61 millivolts. If you remember, we were previously measuring 69 millivolts. A tip for accurately measuring power rails is to always use the most sensitive vertical resolution possible. It will result in a measurement with the lowest noise from your scope. And your scope will never make a measurement with more accuracy than the noise of the scope and probe measurement system. If we use the same probe, but this time with a shorter ground, a ground spring, across the bypass capacitor, we get a significantly more accurate measurement. This time we measure 32 millivolts of peak-to-peak voltage. Remember, we started with a measurement of 69 millivolts. We've already improved our measurement result by 50% by using better grounding. For many engineers who weren't surgeons in previous lives, it can be difficult to hand-hold the probe steady with one hand while operating scope with the other hand. Probe positioners, both 2D and 3D, are great for measurement stability versus trying to make a measurement while holding a probe by hand. I'm a big fan of 3D probe positioners and use one of them often.
For the second approach, we're going to measure the power rail using a passive 1-to-1 probe. Passive 1-to-1 probes are known for having very, very low noise. What are some key advantages and disadvantages of using a 1-to-1 passive probe? As mentioned, their 1-to-1 attenuation ratio means that they're going to have lower noise for a better measurement. Passive probes are significantly lower in cost than active probes. They have excellent loading at DC. The 1-to-1 attenuation ratio means that I can use the most sensitive scale on an oscilloscope, and like their 10-to-1 passive brethren, there's a variety of different connection methods that are very convenient. A key disadvantage is that they have bandwidth limiting. In the case of the Rohde Schwarz ZP1X, for example, it's bandwidth limited to 38 megahertz, meaning that any tones in my power rail that are above this frequency will be attenuated and measurement results may be underreported. In addition, there's no built-in offset in the probe, so my offset will be limited to whatever is available natively in the oscilloscope.
For larger DC rails, such as 3.3 volts, 5 volts, or larger, oscilloscopes typically don't have enough built-in offset to allow a user to put that rail in the center of the oscilloscope display and use a real sensitive resolution to get a more accurate measurement. In the case that I'm looking at, I could only use 200 millivolts per division, and I know my measurement result isn't great here. So to compensate, I've turned on AC coupling in the oscilloscope, which eliminates the DC portion of the signal and just shows me the AC portion of the signal. There's a couple of key drawbacks to this technique. Number one is I can't tell what the absolute DC value is anymore. Secondly, I miss low frequency drifts. The advantage is that I do get a better measurement result because I have significantly lower noise by using the most sensitive vertical resolution. In this case, I've also used a ground spring across the bypass capacitor to get low noise, and we're measuring just 12 millivolts peak to peak versus a 69 millivolt peak to peak value that we had originally with the 10-to-1 probe and the long ground lead. You might start wondering in your mind, is this measurement correct? That's a huge difference. It really depends. If I have signal content on my device that exceeds the bandwidth limit of the 1-to-1 passive probe, in this case 38 megahertz. So you can see some of the drawbacks of using a 1-to-1 passive probe with limited bandwidth and no built-in offset. Let's look at the third approach, which is using a 50 ohm cable. I visited several development teams that employed this technique. The thinking that went through their minds is the 50 ohm path of an oscilloscope typically has much quieter, lower noise than the 1 megohm path. They can use a cable that has a 1-to-1 attenuation, which is also good for low noise, and users can design in an SMA connector or solder in a 50 ohm coax pigtail to easily connect and make highly repeatable measurements.
What are some key advantages and disadvantages of using the scope's 50 ohm path for power rail ripple and noise measurements? An advantage is, for a number of scopes on the market, the 50 ohm scope path has less noise or is quieter than the 1 megohm path. And as users can solder in a pigtail or use a direct connection with an SMA, it has greater measurement repeatability than trying to handhold a probe. A key disadvantage is at DC, this technique has 50 ohm loading on power rails, which typically have impedance on the order of a milliohm at DC. So we're going to see a change in the overall DC value based on this loading. Secondly, this connection method is reliant on the built-in offset capability in the scope. There's no additional offset provided. As most scopes don't have enough built-in offset on the 50 ohm path, engineers will often go into coupling and change from DC to AC coupling. This essentially eliminates the DC levels, allowing the user to just focus on the AC characteristics of the signal. Let's look at the measurement result using this technique. As the scope doesn't have enough built-in offset, we can only scale vertically to 200 millivolts per division, or 2 volts full screen. This produces significant measurement noise and results in the biggest measurement reading we've seen to date. It's 79 millivolts peak-to-peak voltage. In addition, note the rail voltage of just over 3 volts. Our 50 ohm path has loaded the rail and changed its value significantly. Just like with AC coupling, a way to compensate for the lack of built-in oscilloscope offset in this technique is using a blocking cap. Again, it gets rid of the DC component and we can just measure the AC characteristics of the power rail. In this case, we're able to zoom in at 1 millivolts per division, so 10 millivolts full screen,
and I get an amazing peak-to-peak measurement of 4.7 millivolts. This is by far the lowest reading we've had thus far. Is it correct? Let's think a little bit about a blocking cap and what it does. For this particular blocking cap, I just grabbed it. It didn't have markings on it in terms of bandwidth, so I did a quick characterization of it, and I found that it had a roll-off at about 20 megahertz. This means any signal on my power rail greater than 20 megahertz is not presented to the oscilloscope, so the measurement will indeed be underreported. And another disadvantage is, again, we don't know what the absolute DC value is. So just like with AC coupling, using a blocking cap with a 50-ohm cable is not recommended.
Sometimes it's easier to have a visual example of this. Here's a look at blocking caps for AC coupling and some of the measurement problems that they create. On the image on the left, again, if we have a signal that has some type of low frequency drift associated with it, when we use either a blocking cap or AC coupling on the scope, what we'll see is the picture on the right. Again, it completely attenuates the DC values, and so we only see the AC components. Let's take a look at the fourth approach. This approach is still relatively new. The first power rail probes appeared in 2015, and today all major oscilloscope manufacturers offer one or two versions of the probe. Oscilloscope manufacturers offer a variety of different probes. Some are general purpose and perform well for a variety of tasks. Others, like the power rail probe, are specialized and excel at just a few tasks. In the case of the power rail probe, it's uniquely designed to measure power rails. Let me talk a little bit about power rail probes and provide an analogy of them being a specialty tool. I absolutely love home projects, particularly ones that I haven't previously done. A couple of years ago, my daughter asked me to install some laminate flooring in her townhome. I was happy to do that, and I quickly found that one of the biggest challenges was how to work with door jambs. I had a number of general purpose saws at my disposal and found that none of them were particularly well suited for that task. I did a quick search on YouTube and found a wonderful tool called a jam saw and a couple of very short educational videos that allowed me to figure out how to use a jam saw. I invested in one and found in a minute it did an absolutely wonderful job at making a very small cut, exactly the height of laminate flooring, enabling the flooring to go perfectly under the door jamb. Without this tool, this job would have been incredibly difficult. With the tool, it was very, very easy. It could be done in about a minute with spectacular results. A power rail probe is similar to this. It's a specialty tool. It's not made for doing general purpose tasks, but it's absolutely incredible and perfect for making power integrity measurements. What are the key advantages and disadvantages of using power rail probes? A key advantage is the one-to-one attenuation ratio. This is going to result in a low noise measurement and enables us to use the most sensitive vertical setting on the oscilloscope. Power rail probes incorporate built-in offset that allows them to go beyond what's natively available in an oscilloscope. They have excellent loading at DC and typically have a variety of different connection methods. A disadvantage for them is it is an additional initial investment. To achieve full bandwidth, they typically require solder-in connections, and the power rail probes really are not useful for measurements outside of power integrity. As an example of power rail probes, let's look at two that are available from Rohde Schwarz, the ZPR40 and the ZPR20 power rail probes. Both scopes share all of the same specifications and characteristics with the exception of bandwidth. The ZPR40 has 4 gigahertz of bandwidth, while the ZPR20 has 2 gigahertz of bandwidth. They both have a dynamic range of 850 millivolts, meaning that they can look at peak-to-peak voltages up to 1.7 volts. They have an integrated offset of plus or minus 60 volts, and both of them have very, very low noise, adding typically about 10% more noise than what the scope would have if it had no probe attached to it. Both of them have great input resistance at DC at 50 k ohms, meaning that they will have minimal impact on the overall DC value. And they have some capabilities that we'll talk about in a little bit with a Rohde Schwarz probe meter and AC and DC coupling. Power rail probes by nature are active probes, meaning they have an amplifier in the probe itself. The amplifier makes a connection it terminates with an SMA connector where it has an SMA cable that's part of the probe kit that connects to that. And then the other end of the SMA can connect to a 50 ohm coax that could be soldered onto a target board. You can see an example of that in the lower right hand. An advantage of soldering in is you get to preserve the full bandwidth. I've also seen some development teams, there's a picture of it on the top part, that will just use a straight SMA connector. This requires a development team to think about their board design initially and to have a desire to route out power rails to SMA connectors. For users that don't give forethought in terms of soldering in a connection or providing an SMA, there's also a browser capability. So the amplifier part of the probe has a SMA cable that connects to a browser, and it can be used to quickly move across different power rails to measure them. One of the key things to note about the browser is the browser typically does not have full bandwidth. In the case of the Rohde Schwarz browser, the bandwidth is 350 megahertz. One capability to consider for a power rail probe is an integrated voltmeter. With Rohde Schwarz power rail probes, this is called a probe meter. It's a separate 18-bit ADC inside of the probe that runs in parallel to the scope's main ADC. It allows the probe to accurately monitor the DC values of rails that it's connected to. This ADC is 18 bits and it has a 0.05% DC accuracy, 10 times more accurate than a scope's analog channels. The key advantage is it eliminates the need to attach a separate digital voltmeter in parallel to a scope to accurately measure DC values. Let's connect the power rail probe to the scope and a test board. The probe meter shows a highly accurate DC rail value of 3.29 volts. This is really close to the 3.3 volt value we anticipated. The scope software has a very handy feature to copy the probe meter DC value to the scope's offset, instantly bringing the waveform near the center of the screen. This is unique in the industry and something that can be really, really helpful when looking at power rails. So what does our noise and ripple measurement look like with the power rail probe connected? We're able to zoom in at 1 millivolts per division, so we have 10 millivolts full scale. And even though we have 2.5 gigahertz of bandwidth, we're measuring just 6 millivolts peak-to-peak voltage. Remember what we started out with? 69 millivolts. From the probe meter, we know that the absolute DC value is 3.29 volts. The DC rail is likely to be very close to this value with no probes attached. With a soldered-in connection, we get a highly repeatable measurement result as well. Let's directly compare the measurement results from the 4 techniques. In the first case with a 10-to-1 standard passive probe, we measured 69 millivolts peak-to-peak voltage. We now know that this technique severely overestimates the amount of noise and ripple we have on our rail. Our second technique was to use a low bandwidth 1-to-1 passive probe. We achieved a peak-to-peak voltage measurement of 14 millivolts, but have concerns about under-reporting the measurement value based on bandwidth limiting and the lack of built-in offset, which limited our ability to use the most sensitive vertical scale. The third approach that we had was using a 50 ohm path on the scope with or without AC coupling or a blocking cap. This achieved measurement results of 15 millivolts, but we were unable to see the DC value when we used AC coupling or the blocking cap, and unable to see drift, and this technique had a dramatic impact on the absolute DC value due to the 50 ohm loading. Hence, this method, as well as this first method, are not recommended. The fourth method that we used was using a power rail probe. We achieved a peak-to-peak voltage measurement of 6 millivolts, by far the best value of any of these, and we now know the most accurate. Accuracy was based on the low noise 1-to-1 attenuation ratio, the excellent loading at DC, the high bandwidth to incorporate any signal content on the power rail, and the ability for the power rail probe to have a large amount of built-in offset to compensate for limitations in native scope built-in offset.
Power rail probes can be great at looking at transients or a coupled sources that are riding on power rails. In the case of Rohde and Schwarz oscilloscopes, I'm showing an RTO oscilloscope with a ZPR20 power rail probe that allows users to quickly characterize the power rail and any unwanted sources that are on that rail. The very fast update rate, in this case 1 million waveforms per second, will help users find worst case violations in both the frequency domain and the time domain.
A common question for development teams is, how much bandwidth do I need to measure my power rails? They're DC, right? Well, it actually depends on the power rail, and often it's hard to determine how much bandwidth you need until you hook up and start measuring. Here's an example of a power rail from a device with a 20 megahertz bandwidth limit filter turned on the oscilloscope. We're measuring a peak-to-peak voltage of 32 millivolts. Is that accurate? Well, it depends. One of the best ways of seeing how much bandwidth you need is simply to start with more bandwidth and see where your wave shape changes. So in this case, I now am looking at 200 megahertz of bandwidth. I can see changes in my wave shape. I have spikes or transients that were riding on the power rail that I couldn't see when I had 20 megahertz bandwidth limit. This tells me that I need at least 200 megahertz of bandwidth, but my peak-to-peak voltage didn't change sufficiently. Let's take another peak when we turn on 1 gigahertz of bandwidth. Now the signal looks very, very different. The transients are more pronounced and there's more of them. So for this particular power rail, there were transients that were riding on the power rail between 200 megahertz and 1 gigahertz. I'm now making a measurement peak-to-peak of 40 millivolts, and I have a lot more confidence that this one is accurately. If I increase bandwidth to 2 gigahertz or 4 gigahertz, my peak-to-peak measurement doesn't change, the wave shape doesn't change, so I'm confident that this is sufficient. Another good technique is simply to turn on an FFT and enable full bandwidth and to look at the various tones associated with the power rail. It'll give you a view of how much bandwidth is needed. Here's another method for determining how much bandwidth you need for power rail measurements. On this particular display, on the top of the display, I can see the time domain view of the power rail. And on the bottom, I've turned on the FFT associated with that power rail. I've done a gated FFT, so I'm only looking at the portion of time on the top associated with when I see large spikes on my power rail. I can quickly look at the FFT and determine where I have additional signal content that might be from transients riding on top of the power rail. This is an excellent way to quickly visualize how much bandwidth you need for a measurement, and it incorporates transients riding on the power rail unexpectedly.
Let's take some additional time to get more insight. If we adjust the time base of the scope to a slower setting, 4 milliseconds per division, we can see some periodic peaks in our power rail. What's the cause of these? We haven't put a load on yet, so it must be some type of signal from the board itself coupled onto the power rail. If we connect 2 additional passive probes to the I2C bus on the test board, we find that there's a direct correlation. Every time there's serial packet activity, the power rail has a spike. Let's turn on the scope's FFT. The Rohde Schwarz RTO 2000 has an incredibly power FFT that's also very quick. We see a tone at 10 megahertz and a third harmonic at 30 megahertz. I've taken out a near-field probe and connected it to the oscilloscope. I'm using the largest loop, and when I move the probe to a certain spot on the board, I find a pronounced 10 megahertz frequency. The EMI coupling must be from this 10 megahertz source. And if I pull out a magnifying glass, I can see that it's an oscillator and it's located fairly close to the power rail. This is kind of a neat exercise. Again, we've looked at the power rail, done some initial measurements on looking at ripple and noise on it. We were able to look using the FFT and our protocol capabilities of the oscilloscope to notice that every time there's a packet at 10 megahertz, that there's a voltage spike on the power rail, and now we've been able to use a near-field probe to isolate the cause of that. Power rail probes are also great connected to power rails when combined with a current probe for load step response measurements. Here's an example using our RTO 2000 with a power rail probe and a current probe. And we can see as there's a significant change in the current that we get a voltage drop on our power rail, and we can precisely measure both the drop of the voltage and look and see how it correlates to the current increase.
A related measurement topic is power sequencing. A common measurement challenge for power sequencing is not having enough analog scope channels to sufficiently track a number of power rails as they turn on and off. One of the ways that Rohde Schwarz addresses this particular challenge is by offering low bandwidth 4-channel faceless oscilloscopes that can be added onto an existing RTO oscilloscope as an example to create a 12-channel measurement system. Each of these low bandwidth oscilloscopes has internally an 18-bit ADC that produces a very high precision measurement. Inside of Rohde Schwarz, we found this approach to work extremely well as we've tested power sequencing on our devices as we turn them on. We've talked about a number of different techniques and methods for making more accurate power integrity measurements. On the web, there's a variety of different sources that are available to you from Rohde Schwarz that will have additional information on these methods and our solutions for power integrity measurements.
I appreciate your time, and I'm open for questions.
Great, thanks so much, Joel. So I'm going to pass the floor over to you to answer some of these questions.
You bet. The very first question is, will a 10-bit or 12-bit scope allow me to make better power integrity measurements than an 8-bit scope? The answer to that is it depends. Typically, when we're looking at the very, very small amount of peak-to-peak voltages on a power rail, it's noise that dominates the measurement and not the resolution of an ADC in an oscilloscope. So the noise associated with the oscilloscope rather than an ADC. So it depends on the oscilloscope and how much noise it has. But typically, all three of those will produce results that are more dependent on the noise associated with the oscilloscope than the ADC resolution. The second question is, you didn't talk about memory depth. How does a scope's memory depth impact my ability to make accurate power integrity measurements? Memory depth allows oscilloscopes, greater memory allows oscilloscopes to capture more time. The other benefit that deep memory has is the ability to maintain a higher bandwidth with slow time-based settings. So you can think about an oscilloscope as you turn the time base slower and slower to collect more information or more time, which is consistent with power rails that typically need a lot of time. At some point in time, the oscilloscope runs out of memory and it says, you know what, I don't have any more memory. What I'm going to do is I'm going to drop my sample rate in half. You turn the horizontal scale again and it drops the memory in half again, etc. Oscilloscopes that have deeper memory are more capable of enabling higher bandwidth over those changes to slow time bases. Next question is, why is a specialized power rail probe better than an active differential probe that I already have? Really good question. Power rail probes are designed with a 1-to-1 attenuation for very low noise. Differential probes that exist in the market outside of this typically are able to see higher peak-to-peak voltages, but they also have more noise associated with them because they don't have a 1-to-1 attenuation. Next question is, how much does a power rail probe cost, and can it be used with any scope? From a Rohde Schwarz perspective, our power rail probe, the ZPR20, starts at just over $3,000 US, and it can be used on any Rohde Schwarz scope that has a probe interface on the front, any of our current ones. The next question is, why does the Rohde Schwarz power rail probe have AC coupling on it if it already has built-in offset of plus or minus 60 volts? The AC coupling is an optional control that a user can set on the probe. And what it allows the user to do is quickly move from rail to rail to rail and to measure noise and ripple without worrying about drift. So it's a little bit easier. You don't have to scale the waveform on the scope. You can quickly move it around to see what's happening there. Do any other power rail probes have the integrated probe meter? This could be very useful for quickly troubleshooting. So the Rohde Schwarz power rail probes, as stated in the webinar, have an additional ADC. It's an 18-bit ADC integrated in the probe itself. It digitizes the DC value of the power rail probe, sends that back to the scope, and it's 10 times more accurate for DC measurements than a traditional analog scope input is. I am not aware of any other power rail probes in the market that have that capability. The next question is, can I use a power rail probe to measure small amounts of current across a resistor? The answer to that depends. It's actually a really good question. A number of users have a desire to do current profiling or measure very, very small amounts of current. And one idea is to use a power rail probe, which again has very low noise, to measure across a shunt resistor. The answer to the question really depends on your design and the shunt resistor. Power rail probes that are in the market today are single-ended, so it would require that a shunt resistor at one end be connected to earth ground. The second consideration has to do with common mode rejection ratio. The probes are measuring very, very small amounts of noise and ripple, and if the DC value changes, it has a relationship on the probe's ability to see and accurately measure those very, very small signals. So the answer to that is depends. I have one last question, and that is, how does the scope's update rate impact power integrity measurements? When people talk about update rate for oscilloscopes, it has to do with the scope's ability to acquire, process, and display acquisitions. Every time it does this, we'll call it 1 acquisition per second. If a scope can do that 100 times a second, then it would have an update rate of 100 acquisitions per second. If it can do it 100,000 times a second, it would have an acquisition rate of 100,000 times per second. Depending on your particular system that you're trying to measure, you might have a greater need to measure more real time to make sure that there's not any transient events that you're missing on the power rail. And for these cases, it's important to have a scope that has very fast update rate. Update rate is typically specified for scopes manufacturers as a value when the scope is essentially after a default setup or a preset. And as you turn on additional memory, measurements, and other types of things, the update rate will slow down to some degree, depending on the scope's architecture. That degree might be greater or less. But in general, the faster the update rate, the better you'll be able to get statistical convergence on peak-to-peak and noise measurements on an oscilloscope with power rails, and you'll be better equipped to find transients that might be riding on top of the power rail. Okay. And I think that does it for all of the questions. Marla?
That's great. Thanks so much, Joel. And we'll be sending out an email with the recording. So if you do want to forward that on to anyone else who you think may be interested in it, or if you want to rewatch it yourself, then you'll have that in your email in the next couple of days. And if you do have any questions, you can reply back to my email, and I'll be happy to point you in the right direction and get answers for you. So thanks again, Joel, for your time, and I hope everybody has a great day. Take care.